Welcome back, everybody. We're going to talk about transition states. So if we have a reaction where a molecule is becoming another molecule, and we have two types of reaction. We have exothermic and we have endothermic. Two types in terms of heat. And we're talking about potential energy here. And in an energy diagram, as we mentioned earlier, that will be the y-axis. So if we have an energy diagram, there's the reaction progress here. Similarly over here. And exothermic starts with high potential energy and ends at a much lower potential energy. And why is it called exothermic? Well, you do remember that law of conservation of energy says that energy cannot be created nor destroyed. So if the potential energy is going down, which it is, then what energy is compensating by going up? That's the heat energy. The energy of the surroundings will warm up by the same amount the reactants went down when they became products. So that's an exothermic reaction. Endothermic starts low and ends high. Looks like a mirror image. So we have reactants on the left in both, and products on the right. Hello. Got my stray dot there too. Don't ask about the stray dot. Okay. What happens during a reaction is there's a transition from reactants to products. Makes sense. The transition state is the highest energy transition between the reactants and the products. So the transition state in this reaction lives up here. Transition state. And the symbol for it is square brackets and telephone pole. Don't know if I'm going to get all of that. Didn't think so. You're being mean. Start over. Hello. Okay. Sorry, I'm talking to my computer. Transition state over here. Now, just for motivation, we're going to call this an early transition state, and this one a late transition state. You have no idea why. So forget we're talking about chemistry for a second, okay? Just maybe even close your eyes. Pretend you're blindfolded, so you can't see anything, and you're put in a room, and you're told that somebody's going to come in the room, and you just have to tell one fact about this person. Is it a young person or an old person? But you can't look at them. You just have to use all your other senses to figure it out. Okay? So here's the first scenario. Door opens, you hear that. Then you hear a whole bunch of scurrying, and then bam, the door shuts. Okay? That's scenario one. Scenario two, door opens, you hear some very slow shuffling, maybe some grunting noises, you never know, and then the door closes. So in which scenario are you guessing that a young person entered the room? I'm hoping you're saying scenario 1. And in the other scenario, that'd be an old person. If you're a young person, are you closer to the beginning of your life? Are you early in life or late in life? You're early in life. If you're an old person, you're later in life. Now let's use this diagram. Let's just use the energy, because you use the energy to make your conclusions, right? The energy of the scurrying and lots of things going on just gave you a sense of young. And you just used energy to base that decision. We're going to use energy to base these decisions too. We have 3 energies. We have the energy of the reactants, the energy of the transition state, and the energy of the products in both examples. I have the same question for you for both diagrams. Is the energy of the transition state closer to the energy of the reactants or products in this first diagram? It's only this far away from the reactants. It's this far away from the products. We call it an early transition state, like I said before. Based only on its energy, I'm guessing that this thing will appear. Its appearance will be closer to the appearance of the reactants than that of the products, based on the fact this is an early transition state. Its energy being closer to the energy of the reactants. Over here, the energy of the transition state is much closer to the value of the energy of the products. I'm going to call that a late transition state. These two, I'm just going to highlight that with my highlighter here. The energy of these 2 species is the closest. And we're going to call that an early transition state. Okay, my pen's ignoring me. I don't like it when it does that. Still, wow. That's still on the highlighter. Sorry, I'm having a day. Okay, and highlighter again. Give it another shot. And go with these 2. In the second diagram, the energy of the transition state is closer to the energy of the products. Products are at the end, right? That's late. Reactants are at the beginning. That's early. This is late. Pen, not pen. Pen. Oh, I have to click here. I've lost my mind. Pen's there. Okay. Green. Late. TS. First one. Early TS. Yes, you can go ahead and memorize that exothermic reactions have early TS and endothermic reactions have late TS, but does that give you any understanding of chemistry? Do you get any satisfaction when you memorize a fact like that? I don't. And then test day, you get them backwards and you have no idea why. And you got to remember, you're talking about, hey, their energies are closer in this diagram. So the transition state, energy closer means its appearance should be closer. We'll know what that means shortly. In fact, let's just look at a reaction where we can have early and late transition states for the same reaction. Let's do a typical reaction. We'll have a radical reacting with X and Y to generate Rx plus Y dot. And the mechanism works like this. And the transition state looks like this. Before we do the transition state, I have a question for you. Only one of the atoms out of or one of the parts out of the three. Here are the three parts: the R part, the X part, the Y part. Which of those three, R, X, or Y, is the one that's in transition from one molecule to another? And I hope you see the answer to that question is X. It's moving away from this molecule towards this. The question is, in the transition state, is it closer to Y or is it closer to R? Early in this reaction, it's closer to Y. Late in this reaction, it's closer to R. Sorry, it's R. We're talking about X. So fact one, X is in transition. Just look at the mechanism. Don't memorize it. Just look at the mechanism and say, oh, X is the only one that's moving. So if this was a reaction that wasn't exothermic or endothermic, X would be in the middle. Okay. All right. So in the transition state, it looks like the reaction. You got R on one side, and on the other side is Y. And we'll do early and late. We'll do early first because it was first in the diagrams. And we'll do late next. And here we go. Copy paste. X is transitioning. So late, it's very close to the R. And what's the transition between not having a bond at all? There's no bond from R to X here, is there? And having a covalent bond. What's the transition between no bond and a real bond? And the answer is a partial bond. The transition between no bond and a real bond is a partial bond. So late, X is real close to R. Real close to R with a partial bond. And there's your X. And it's very far away from Y. It began with Y, and late on, it's nowhere near Y at all. Look, do you see it attached to Y here at the end? That's late. Late equals products. Early equals reactants. So I don't want to see it anywhere near Y in the late reaction. And I want to see it real close to Y in the early reaction because that's where it started. It started close to Y here early on. So it's not that hard, is it? Identify the transitioning atom. Your reasoning based on early or late is based on exo versus endo. If it's early, have it close to where it started, close to Y. If it's late, have it close to where it ends. It ends with R. And that is the discussion that should help us answer our question. So we're going to see page 6 in our answer portion. See page 6 for E and F. See page 6 for discussion because only 3 of you are here for the original lecture here. And you've got to give this argument. You got to talk to me about prop 2. I don't care about prop 1 anymore. Once you identified prop 2 is the rate determining step because it was less exothermic, that's the one we need to talk about. So we're going to diagram that transition state, and it's endothermic. I'm going to try something with my hands that I don't know if it's going to translate very well. Prop 2 and a diagram. Nice. This is E and F. Which one has the diagram, E or F? F. And E, your answer is here. In an endothermic reaction, the energy of the TS. What's TS again? Oh, transition state. No, put it over here. Of the TS is closer. And I don't have this memorized. Energy of the what? Reactants or products? I don't know. It's an endothermic reaction. That's what I know. Energy of the, oops, I'm starting to write random stuff. All right, I'm going to talk to myself because I'm looking at the picture on the screen, and this is my right hand and it's on my left. Okay, I'm going to forget I did that. Reactants, products, reactants. Okay, reactants here, this hand that's moving, reactants, products, endothermic, reactants, products. I got it. Okay, good. Reactants here, products here. Which the transition state's above both my hands, right? Oh, look at that. The transition state's the top of my head. I like it. I can't point to the top of my head right now. Which hand? Oh gosh, I'm losing track. Reactants or products is closer to the top of my head. Products, closer to the top of my head. You like that? Products are at the end, aren't they? Products, they're late. Endothermic transition state is closer to the products, to the energy of the products. And I lost my pen. Products. And that's not the end of your answer. There's a very sophisticated argument here. In an endothermic reaction, the energy of the transition state close to the energy of the products than, ew, that's a big A, the reactants. So you got to acknowledge you're using energy to estimate appearance. So TS should resemble. Did I say reactants and products? I got to do this off screen. Endothermic. I had the right words earlier, and yeah, product. I have the right words on the screen. TS should resemble products more than reactants. So the TS should resemble. That's different than energy, but we used energy to make the decision. More. How's that for an answer? Now, get that reaction back on the screen. I need the BR, which is, look, BR's transitioning from here to here. I need the BR to be real close to the carbon. In fact, you want to make it better than the notes page? Let's have the product over here. Chicken foot. And I gained a carbon when I did that. Start over. I don't know why I did that too. We're making a bond from this carbon to a bromine. And at the end of the reaction, TS closely energy product in the reaction, so TS should resemble product. No, we have a word for that. I didn't even use the word. It's late, right? If you're resembling products more than reactants, you're late. And what's it transitioning away from the BR? Away from the F. So keep this going here. I just need to see it any amount closer to the product than the reactant. And then I'm a happy man. And I don't want to rush termination steps. And we do have more things in this chapter to talk about. So I've given you enough to, definitely enough to digest over the weekend. And I expect you to have chapter 8 read before the end of the weekend. And we will continue this discussion at that time. And I wish you all well. And until Monday, I will see you then.